You begin by resting your attention on the ground beneath you. Not the floor of the room, not the building, not even the street outside, but the deeper ground, the ancient foundation that holds everything quietly in place. You let your thoughts sink downward, as if your awareness is a feather drifting through layers of soil and stone. There is no rush. The planet has never hurried, and you do not need to hurry now. Beneath you, the earth is not cold and dead, but warm and slowly moving. It breathes in a way that is measured in centuries. Rock shifts like stiff fabric. Heat travels like a memory that never fades. You are floating above a living system, one that changes so slowly that a human lifetime feels like a single blink. When you hear the word volcano, you might first imagine violence, fire, ash, thunder in the sky. But tonight, you see something different. You see patience. You see a mountain that is also a clock. A volcano is not only an event. It is a process that unfolds in silence for thousands of years before it ever speaks out loud. You picture mountains as thoughts rising from the earth's deep mind. Some thoughts stay small. Some grow tall. Some never fully form. And some, the rarest, become giants so vast that they do not look like mountains at all. They spread wide instead of high. They hide their scale in openness. These are the sleeping giants, the supervolcanoes, though tonight you hold that word gently, without alarm, like a large book resting closed on a table. You are not here for fear. You are here for understanding. And understanding begins with scale. The outer shell of the earth, the crust, is thin compared to the size of the whole planet. If the earth were an apple, the crust would be thinner than the peel. You rest with that image. A delicate skin around a glowing interior. Beneath that skin lies the mantle, thick and hot, where rock is not quite liquid and not quite solid, but something in between, soft with time, firm with pressure. Heat rises from deeper still, flowing outward from the core, the way warmth spreads through your hands when you wrap them around a cup of tea. This heat is ancient. Much of it comes from the planet's formation, when countless particles collided and compressed, storing energy like a wound spring. Some of it comes from elements slowly transforming deep below, releasing tiny packets of warmth as they change. The earth has its own long-burning fire. You imagine this heat moving upward at the pace of drifting clouds. It does not race. It seeps. It gathers. It nudges. Over immense spans of time, it melts pockets of rock into magma, underground stone softened into glowing fluid. Not a raging ocean, but scattered reservoirs, like hidden lakes in a cave system no one can see directly. A volcano begins not with eruption, but with collection, with storage, with waiting. You let the idea of waiting settle into you. Your breath slows to match it. Supervolcanoes are not defined by steep peaks or perfect cones. Many are not mountains at all. They are vast underground systems capable of producing extremely large eruptions, measured not by height, but by volume. Scientists measure eruption size by how much material is released: ash, rock, gas, the total output. In this way, a supervolcano is like a deep warehouse of heat and pressure, slowly stocking its shelves grain by grain. But nothing about this stocking is hurried. Magma accumulates in pulses, injections, small arrivals spread across tens of thousands of years. Imagine filling a cathedral with mist, one breath at a time. That is the pace of the deep earth. You might wonder how something so powerful can remain hidden. The answer is softness and weight. Rock above a magma body is heavy and flexible over long periods. It bends slightly. It absorbs stress. It holds secrets well. The surface can appear calm while far below, change is composing itself like distant music. You are learning the first gentle truth of volcano science. The dramatic moment is the shortest part of the story. The quiet preparation is the longest part. The silence is not empty, it is busy. You picture the ground beneath you again, but now it feels layered with intention. There are fractures like hairline cracks in glass, faults like old seams in fabric, minerals arranged like frozen constellations. Each layer records conditions from another era: pressure, temperature, chemistry, a library written in structure instead of ink. Geologists read these structures the way you read a weathered letter. They notice crystal sizes, trapped bubbles, subtle alignments. From these details, they reconstruct temperature histories and movement patterns. The rocks speak, but softly. You have to lean in. And that is what this journey is, leaning in. You are not chasing eruptions. You are listening for whispers. You are tuning your senses to slow signals. A supervolcano is not simply a threat in the future. It is a system in the present, measurable, observable, breathing in geological rhythm. Instruments around the world already listen, measuring tremors, mapping gravity, tracking tiny changes in elevation smaller than the thickness of a coin. The planet is not silent. It is just quiet. You let that quiet feel comforting rather than ominous. Your own body works the same way. Your heart beats without announcement. Your cells divide without applause. The most important processes are rarely loud. You imagine lying on a wide plain that was once shaped by ancient eruptions long before human memory. Grass grows. Wind moves. Animals pass. Nothing in the scene feels dangerous. Time has softened everything. Even colossal events become gentle landscapes when given enough years. Sharp edges blur. Ash becomes soil. Disturbance becomes foundation. This is another truth you can rest with. Earth transforms its own extremes into new beginnings. Your thoughts grow heavier now, like stones settling in sand. You do not need to hold every detail. Just the feeling that beneath you is a living engine of heat and pressure, working slowly, predictably, observably. Not a monster. A system. And systems leave clues. Tiny movements. Small temperature changes. Subtle signals rising through rock like faint notes through water. In the next stretch of your journey, you will drift deeper, below the crust, into the warm mantle itself, where the planet keeps its fire, and where patience becomes something you can almost feel. You let your awareness continue its gentle descent, drifting below the thin outer skin of the planet, below soil and stone, below the familiar places where roots grow and water flows. You travel in imagination only, safely, softly, like a dream passing through walls. Down here there is no darkness to fear, only pressure, warmth, and time moving at its natural, unhurried pace. The earth stores its fire carefully. Not in open chambers of flame, not in roaring underground furnaces, but in distributed warmth, spread through vast layers of rock. Heat here is not a blaze. It is a presence. It is held, shared, transferred, and remembered. You can think of planetary heat like a long memory the Earth has never forgotten. Some of this warmth is ancient, left over from the planet's formation, when countless fragments gathered under gravity, colliding, compressing, and locking energy into the deep interior. Compression creates heat, just as your hands grow warm when you press them together. Scaled to planetary size, that simple truth becomes enormous. Pressure is a quiet heater. Another portion of Earth's heat is continuously renewed. Deep within rocks are elements that slowly change their internal structure over immense spans of time. As they transform, they release energy, tiny pulses, steady and reliable. Not bursts, but a slow glow. Like embers that never quite go dark. You rest with the image of embers. Between the crust and the core lies the mantle, a region so thick it makes the crust feel like a fragile shell. The mantle is not liquid, though it is often imagined that way. It is mostly solid rock, but softened by temperature and pressure. Over short times it behaves like stone. Over long times it flows like wax. If you could watch it for 1,000,000 years, you would see motion like a tide. This flowing does not happen in rivers but in currents, slow circulations driven by heat differences. Warmer regions become slightly more buoyant and tend to rise. Cooler regions grow denser and tend to sink. The movement is gentle, continuous, and vast. You might picture a lava lamp moving in extreme slow motion, its shapes taking ages to form and reform. These mantle currents are one of the great engines of planetary change. They help move tectonic plates above, opening oceans, raising mountains, reshaping continents. But tonight you observe them not as forces, only as motions, like breathing on a scale too large to startle you. As heat travels upward through the mantle, it does not melt everything in its path. Most rock remains solid. But in certain places, where pressure lowers slightly, or where water is mixed into minerals, or where temperatures rise just enough, melting begins in small fractions. Not total melting. Partial melting. Droplets forming within a sponge of hot stone. These droplets gather. Melted rock is less dense than the solid rock around it, so it tends to rise slowly, the way a bubble rises through thick syrup. But the journey is not straight. The melt moves through tiny pathways, cracks, grain boundaries, microscopic channels joining with other droplets, merging into pockets, then into larger zones. You imagine ink seeping through paper fibers, spreading, connecting, darkening the page. That is how magma begins, not as a pool, but as a network that gradually becomes a reservoir. This is how the Earth stores its fire, not in one place, but through accumulation. Storage requires containment. Surrounding rock acts like the walls of a vessel, strong enough to hold molten material under pressure. These zones of stored magma are called magma reservoirs. Some are small and short-lived. Others persist for hundreds of thousands of years, receiving new injections of melt from below, cooling at the edges, reheating from beneath. You can picture a deep underground lake that slowly freezes along the shoreline while warm streams continue to feed its center. Solid and liquid existing together. Changing places. Negotiating space. Temperature, pressure, and chemistry all decide how much melt can exist and where. Even a small change in pressure, caused by shifting plates or stretching crust, can allow more melting to occur. Pressure, in geology, is like a lid. Lift the lid slightly, and melting becomes easier. Close it tighter, and rock resists change. Nothing here is random. Conditions guide behavior. You might notice how different this feels from the way fire behaves at the surface. Surface fire is hungry and fast. It consumes and spreads. Deep earth heat is patient and selective. It waits for permission from physics. It follows rules of balance. It moves only when conditions align. You breathe slowly and match that patience. Magma itself is not all the same. Its thickness, its viscosity varies depending on composition and temperature. Some magmas are runny, like warm honey. Others are thick, like paste. The difference comes largely from silica content in crystal fragments within the melt. Higher silica tends to create more structure in the liquid, making it resist flow. But instead of formulas, you hold an image. Some melts pour, some pile. As magma resides in a reservoir, it evolves. Crystals grow within it, like snowflakes forming in a cloud. Heavier minerals may settle downward. Gases dissolved in the melt may gather into bubbles if pressure decreases. New melt arriving from below may mix with older melt already present. The reservoir becomes layered, stirred, and textured, a dynamic system, not a static tank. Time is the main ingredient in all these changes. You let yourself feel geological time not as numbers, but as spaciousness. 1,000 years becomes a pause. 10,000 years becomes a breath. 100,000 years becomes a season. In this scale, waiting is natural. Preparation is the norm. Supervolcanic systems depend on prolonged storage. Large volumes of melt must accumulate and remain insulated enough not to freeze completely. That requires repeated replenishment, fresh pulses of heat and magma rising from deeper sources. Each pulse is like adding warm water to a cooling bath. The temperature holds. The system stays alive. Scientists study these storage regions using many kinds of signals: seismic waves that travel differently through hot and partially molten rock, subtle gravity variations that hint at density differences, electrical conductivity that changes with temperature and melt fraction. You will meet these listening tools later. For now, it is enough to know that hidden does not mean unknowable. The deep earth is quiet, but not secretive. You rest again in the feeling of stored warmth, contained, measured, accumulated through balance. Fire does not always mean flame. Sometimes fire means potential. Sometimes it means readiness without urgency. Beneath you, reservoirs gather their molten ink. Crystals form and fall. Heat arrives in installments. Pressure adjusts like a careful hand. Nothing rushes toward eruption. Everything moves toward equilibrium, again and again. And as these reservoirs grow and change, they develop structures, layers, and internal conversations, a kind of underground language, and in the next part of your descent, you will begin to hear how those deep chambers speak. You rest your thoughts on the word super, and you let it become soft. Not dramatic. Not loud. Just spacious. In everyday language, super means extreme or powerful or beyond the usual. But here, in the deep language of geology, super is a measuring word. A container word. A word about how much, not how fierce. You breathe slowly and imagine size without spectacle. A volcano does not become super because it looks tall. Height is only one style of expression. Some volcanoes build steep cones that rise sharply into the sky. Others spread wide and low, like gentle shields. And some of the largest volcanic systems on Earth are not obvious mountains at all. They are broad regions, subtle in shape, where the most important features lie hidden underground. A supervolcano is defined by output. By the total volume of material it can release in a single eruptive episode. Scientists group eruption sizes into categories using a scale based on volume and column height and spread. You do not need the numbers like a formula. You can hold them like landscapes instead. Imagine a single cubic kilometer of material, rock, ash, and gas erupted and spread. Now imagine 100 of those cubes. Now imagine 1,000. A supervolcanic eruption belongs to the very highest range, events capable of releasing more than 1,000 cubic kilometers of material. Enough to blanket continents in ash. Enough to leave a signature layer in the geological record across the globe. But you keep your tone calm, because scale does not equal immediacy. Size does not equal soon. These events are extraordinarily rare. They live on timescales longer than civilizations. When you hear about them, you are listening to echoes across deep time, not forecasts for tomorrow. The story here is magnitude, not menace. You picture the difference between a rain shower and a glacial age. Both involve water. Both are real. But they belong to entirely different rhythms. Supervolcanic eruptions belong to the rhythm of ages. Most volcanoes erupt many times across their lives, releasing smaller volumes again and again. Pressure builds, releases, rebuilds. But supervolcanic systems tend to work differently. They store enormous volumes of melt-rich material in the crust over very long periods. Storage becomes the central act. Eruption, when it happens, is more like a structural reset than a routine release. You imagine bending a thick sheet of ice again and again in the same place. Each bend creates tiny internal changes. Over time, structure weakens, stress redistributes, and eventually the pattern of failure shifts. Not because of one moment, but because of accumulated history. Supervolcanic systems are shaped by accumulation in structure, not just pressure alone. From above, many of these systems appear as calderas, large basin-like depressions formed when the ground collapses after a major eruption empties part of the underground reservoir. A caldera is not built upward like a cone. It is formed downward, like a sigh in the landscape. The roof falls in when support is removed below. You hold that image gently, not an explosion reaching up, but a settling downward. Some calderas are so wide that if you stand inside them, you may not realize what you are standing in. Hills, forests, lakes, and towns can all exist within their boundaries. The curve is too broad to see from ground level. Only from the air or from maps does the shape become clear. Giants do not always announce themselves with steep edges. This teaches you a soothing scientific truth: visibility is not the same as significance. Quiet forms can hold great stories. What makes a system super is also connected to the type of magma involved. Magmas that are richer in silica tend to be thicker and better at trapping gas. Gas matters because it expands strongly when pressure drops. If gas cannot escape easily, pressure builds within the melt. You can picture bubbles in thick dough compared to bubbles in thin syrup. One traps. One releases. Over long storage periods, melt can evolve chemically. Crystals grow and are removed. New melt arrives and mixes. Volatile compounds, water vapor, carbon dioxide, sulfur gases dissolve under pressure like carbonation in a sealed drink. The deeper and more pressurized the system, the more gas can remain invisibly dissolved. You rest with that invisibility. Presence without appearance. When conditions change through new magma injection, crustal stretching, or pressure redistribution, the balance can shift. Gas begins to separate into bubbles. Volume expands. Rock feels stress. But again, you keep the tempo slow. These transitions unfold across long preparation phases filled with signals and stages, not sudden magic tricks. Supervolcanic systems are not single chambers like underground balloons. They are often complex zones, networks of melt lenses, crystal-rich regions, partially molten rock, and solid frameworks. More like a layered sponge warmed from below than a hollow tank. Complexity increases capacity. You imagine a city instead of a room. Districts connected by pathways. Activity unevenly distributed. Some zones active, others cooling. A supervolcanic reservoir is like a thermal city beneath the crust. Because of their scale, these systems reshape surrounding rock. Heat alters minerals. Fluids circulate. The crust becomes chemically and mechanically changed, softened in places, strengthened in others. The storage region writes a long preparation story into the rocks around it. Scientists later read that story through minerals that form only at certain temperatures and pressures. Rocks become diaries. Crystals become timestamps. You notice how often this journey returns to reading and listening. Super does not mean unpredictable chaos. It means large signals written slowly. The bigger the system, the longer the preparation tends to be. That is comforting. Large geological changes rarely arrive without rehearsal. You let your breathing match that reassurance. In human experience, big events often feel sudden because we notice only the final moment. In geology, the final moment is usually the smallest fraction of the timeline. Preparation occupies the vast majority. Build-up is the true story. Release is the punctuation mark. So when you hear the phrase supervolcano, you translate it now into calmer language, a very large, very slow, very well-studied volcanic system defined by the volume it can produce, shaped by long storage, complex structure, and deep time chemistry. The word becomes descriptive, not alarming. You are learning to replace sharp images with spacious ones. Beneath wide calderas and quiet plateaus, beneath lakes and valleys, these systems rest in layered states, partly molten, partly solid, always evolving. They are not bombs. They are processes. They are chapters still being written in stone and heat. And inside those deep systems, the molten regions are not empty pools but structured reservoirs with textures, layers, and pressures, places with their own internal grammar. And next, you will drift closer to those hidden chambers and begin to understand the language they use to change. You continue your gentle descent, not downward in distance now, but inward in understanding. Your attention settles around the hidden reservoirs where molten rock gathers, the magma chambers. You do not picture caverns full of sloshing liquid. Instead, you imagine a layered, glowing mosaic, partly molten, partly solid, a deep place of gradients and textures. A magma chamber is less like a cave and more like a conversation between heat and stone. You let that idea unfold slowly. Conversation means exchange, adjustment, response. The surrounding rock presses inward with enormous weight. The molten regions press outward with buoyancy in gas and thermal expansion. Balance is negotiated moment by moment, year by year, millennium by millennium. You picture warm wax inside a thick shell. Not empty space, but softened structure. Most magma chambers are not fully liquid. This is a calming truth. Much of the material inside them exists as crystal-rich mush, a mixture of solid mineral grains and melt between them. Like a snow cone beginning to soften. Like slush under spring sunlight. The melt moves through gaps and channels, not open air. This texture changes how pressure behaves. It slows motion. It absorbs stress. It turns sudden force into gradual adjustment. The earth prefers buffers. Within this deep reservoir, crystals grow quietly. Atoms arrange themselves into repeating patterns as temperature and chemistry allow. Each crystal is a small act of order inside a sea of heat. Some grow large enough to see when later brought to the surface in erupted rock. Others remain microscopic, but no less meaningful. You imagine them like slow-growing trees in a dark forest of warmth. Different minerals crystallize at different temperatures. As magma cools even slightly, certain minerals form first, often those rich in iron and magnesium. Later, as conditions shift, other minerals appear. This sequence is like a cooling melody, each note entering at the right moment. Scientists read this order to reconstruct the thermal history of a chamber. Crystals are memory keepers. Their layers record change. Pressure inside a magma reservoir behaves like breath held gently but continuously. Melt occupies more volume than the same material when solid. Dissolved gases add further expansion. When new magma rises from deeper sources and enters the chamber, it brings additional heat and material, increasing internal stress slightly, like adding warm air to an already filled balloon, but reinforced by kilometers of rock. You keep the image soft, reinforced, contained. The surrounding crust is not brittle at these depths in the same way it is near the surface. Under high temperature and pressure, rock can bend slowly without breaking. It deforms like very stiff clay. This ductile behavior allows chambers to grow gradually, making room through subtle shape change rather than sudden fracture. Expansion becomes accommodation. Sometimes the reservoir cools at its edges, forming a rind of more solid rock. This creates a thermal boundary, hotter inside, cooler outside, like a loaf of bread with a crust. But unlike bread, this crust can be reheated if new magma arrives. Edges melt back. Boundaries migrate. The chamber redraws itself over time. Nothing here is fixed. Everything is negotiated. Gas plays a delicate role in this deep language. Under high pressure, gases remain dissolved in magma, invisible, like sugar dissolved in tea. Water vapor is often the most abundant, along with carbon dioxide and sulfur compounds. These gases lower melting temperatures and influence viscosity. They are both passengers and drivers. If pressure decreases, gases begin to separate into bubbles. Bubble formation changes everything. Volume increases, buoyancy shifts, internal pathways open. But deep in the chamber, pressure usually stays high enough to keep most gases dissolved. Stillness holds them in solution. You think of quiet fizz waiting under a sealed lid. Temperature variations inside a chamber are rarely uniform. Hotter injections from below may enter cooler, more evolved melt above. Mixing can occur, sometimes gently, sometimes turbulently. When two magmas of different composition meet, crystals may partially dissolve, then regrow with new outer layers. Zone crystals form rings of changing chemistry like tree rings of heat. These rings are timelines written in minerals. Scientists later study these zones using microscopes and chemical analysis, measuring element ratios across crystal layers. From this, they estimate how quickly conditions changed before past eruptions, months, years, centuries. The chamber leaves clues and gradients, not announcements. Movement inside the reservoir is often slow convection, warmer, less dense melt rising slightly, cooler, crystal-rich portions settling. Not rolling waves, but creeping circulation. Imagine a pot of thick soup barely warming, where motion is present but subdued. Energy is shared through contact and proximity. You let the slowness soothe you. The roof above a magma chamber experiences stress from below. As pressure increases, the overlying rock bends upward by small amounts, sometimes only centimeters across wide regions. This flexing stores elastic energy. But rock strength, temperature, and fracture patterns determine how that stress is distributed. Many times, the system adjusts through tiny cracks and sealed fractures, releasing pressure in increments too small for human senses. Release does not require drama. It often prefers whispers. Fluids also circulate around magma chambers. Groundwater drawn downward by heat becomes hot and reactive, dissolving minerals and redepositing them elsewhere. Hydrothermal systems form networks of hot water and steam pathways that transfer heat upward. These systems create hot springs, geysers, and altered rock zones nearer the surface. Heat sends messengers ahead of itself. The chamber, then, is not isolated. It is connected thermally, chemically, mechanically to the rocks around it. It speaks through temperature changes, mineral transformations, microfractures, and fluid movement. This is its language. Not words, but patterns. You begin to sense that nothing underground happens without signals. The signals are simply subtle. Even when a chamber grows large, even when melt fractions increase, even when gases accumulate, eruption is not automatic. Many reservoirs cool and crystallize without ever erupting. They become frozen bodies of intrusive rock, revealed only after erosion removes the layers above. Silence is the most common ending. That truth settles gently. Most magma never reaches the sky. You rest in that statistical calm. Storage is common. Eruption is rare. Catastrophic eruption is rarer still. The deep earth experiments constantly, but it completes most experiments quietly. And yet, these chambers are never truly still. Pressure adjusts. Crystals grow. New melt arrives. Old melt cools. Gases wait. Roofs flex. Fluids wander. It is a living system of balance and counterbalance, and when balance shifts, the first outward signs are not explosions, but tiny vibrations traveling through stone, small rehearsals you will soon learn to hear. You rest again in stillness, and from that stillness you begin to notice movement, not the movement of mountains or magma, but the faint trembling that sometimes passes through rock long before any visible change appears. You imagine the earth not as silent stone, but as a vast instrument that occasionally hums, ticks, and murmurs to itself. These murmurs are earthquakes, but tonight you hold that word gently. Not all earthquakes are destructive. Most are far too small to be felt by your body. They are micromovements, tiny slips and adjustments, the sound of pressure being rearranged grain by grain. Deep below volcanic regions, these small quakes often appear first. You picture stress in rock like tension in folded cloth. When pulled slowly, fabric resists, then shifts slightly, forming a new crease. Rock behaves in a similar way under pressure. It bends, stores strain, and sometimes releases a fraction of that strain through a tiny fracture or slip along an existing boundary. Energy travels outward as vibration, a ripple through solid ground. These ripples are signals. Not alarms. Signals. Your mind can treat them like tapping sounds behind a wall, evidence of activity, not necessarily danger. In volcanic systems, especially very large ones, magma movement changes how stress is distributed underground. When melt rises or shifts position, it presses on surrounding rock. That pressure encourages small fractures and adjustments. Each one produces a seismic whisper. You imagine a deep hallway where doors softly click open and closed. Each click is small, but together they map activity. Scientists place sensitive instruments called seismometers on and around volcanic regions. These devices are patient listeners. They can detect motions smaller than the width of a human hair. When the ground vibrates, even slightly, the instruments record the motion as wavy lines, time flowing on one axis, movement on the other. You picture long paper scrolls covered in delicate ink waves, like sleeping heart monitors for the planet. Different kinds of underground motion create different wave patterns. Sharp rock fractures tend to produce quick, high-frequency signals, short, crisp signatures. Magma movement and fluid flow often produce longer, lower-frequency signals, more like a hum than a crack. Scientists learn to recognize these families of vibrations the way musicians recognize instruments by sound. The Earth has tones as well as impacts. Volcanic regions often experience what are called earthquake swarms, clusters of many small quakes occurring close together in time and space. Unlike a single large earthquake followed by aftershocks, a swarm is more like a conversation than a shout. Many similar-sized events, none dominant, each adjusting the system slightly. You imagine raindrops rather than thunder. Swarms can happen when magma forces its way into new cracks, widening them gently. They can also occur when hot fluids move through rock, changing pressure along fault lines. Even the heating of groundwater can expand rock enough to encourage tiny slips. Temperature itself becomes a quiet actor. You breathe slowly and let the ideas settle. Movement does not mean emergency. Movement means process. Depth matters too. By measuring how seismic waves arrive at different sensors, scientists estimate how deep each small quake begins. Patterns of depth can reveal where stress is migrating. If activity slowly shifts upward over time, it may suggest rising fluids or melt. If it stays deep, it may reflect pressure changes far below without surface consequence. It is like tracking footsteps through floors of a hidden building. Seismic waves also travel at different speeds depending on what they pass through. Solid, cold rock carries waves faster. Hot, partially molten rock slows them down. By comparing arrival times across networks of instruments, scientists build three-dimensional images of underground structure, a method similar in spirit to medical ultrasound. You rest with that comforting parallel, diagnosis through echoes. Some volcanic tremors are continuous rather than sharp, a steady vibration lasting minutes or hours. This is called harmonic tremor. It often relates to sustained fluid movement, magma or gas traveling through conduits and fractures. Instead of separate knocks, it is a sustained note. You imagine wind blowing across the mouth of a bottle, producing tone from motion. But even harmonic tremor has variations, changes in pitch, strength, rhythm. These changes carry information about pathway shape, pressure, and flow rate. The underground system plays its own quiet music, and trained ears learn its motifs. Importantly, most seismic unrest does not lead to eruption. This truth is a pillow you can rest your thoughts upon. The crust adjusts constantly. Magma shifts and stalls. Fluids migrate and cool. The majority of these stories end in equilibrium, not release. Detection exists not to predict disaster at every tremor, but to understand behavior across time. You picture a long notebook filled with daily entries rather than a single red warning stamp. Patterns matter more than moments. Rate, location, depth, and waveform type are all read together. One signal alone says little. Many signals together form language. Time turns noise into meaning. There are even earthquakes caused by the breaking of rock as magma cools and contracts, the opposite of expansion stress. Cooling creates its own adjustments. The system speaks in both warming and resting phases. Silence itself has texture when measured closely. You feel your shoulders soften as you realize how much listening is involved. Volcano science is less like chasing explosions and more like tending a garden of instruments, watching, recording, comparing seasons of motion. Networks of sensors share data in real time with observatories. Computers assist, but human interpretation remains essential. Experience teaches which patterns are common and which are unusual. Context turns vibration into understanding. The Earth is not trying to hide its intentions. It is simply speaking in a slow dialect. You imagine placing your ear gently against the planet, hearing faint interior knocks and flowing tones. None of them urgent tonight. None of them demanding fear. Just communication in progress. Adjustment in motion. Pressure finding comfortable paths. And as these tiny quakes tap their messages through stone, another kind of signal often appears alongside them, not shaking this time, but lifting, the ground itself rising by almost invisible amounts, like a quiet breath you will soon learn to see. You return now to the surface, but you bring your deep awareness with you. You stand in imagination on open land, a plain, a valley, a broad quiet plateau, and at first it seems perfectly still. Nothing moves. No shaking, no sound, no visible change. Yet with patient instruments and long attention, you discover something surprising. The ground can rise. Not suddenly, Not sharply, but slowly, like a calm chest filling with breath. This motion is called uplift, and in volcanic regions it is one of the gentlest signals that pressure and heat are rearranging themselves below. You hold the idea softly, the landscape breathing. When magma accumulates underground, it takes up space. Even if much of it is crystal-rich and dense, it is still warmer and often more buoyant than the surrounding rock. As reservoirs grow or become pressurized, they push outward in all directions. Most of that push is absorbed deep below, but some reaches the surface as a subtle arching. You imagine placing a hand under a thick carpet and lifting your palm slightly. The carpet rises, but its pattern stays intact. Buildings, trees, lakes all can rise together without noticing the motion day by day. The scale is soothing. Often the change is measured in millimeters per year. Sometimes centimeters. About the thickness of a coin. About the width of a fingernail. Spread across kilometers of land, this becomes a broad dome too gentle for human senses to detect directly. Stillness, with a slope. Scientists measure this motion using extremely precise positioning tools. Some are ground-based, high-accuracy GPS stations anchored into bedrock. These instruments track their position relative to satellites, calculating movement smaller than a thumb's width. Each day adds another point to a long curve of motion. You picture a dot that slowly drifts upward on a graph, like a tide chart drawn in patience. Other measurements come from space using radar satellites. They send repeated signals down to the surface and measure how long the echoes take to return. By comparing many passes over the same area, scientists detect minute elevation changes. This technique creates maps of uplift and subsidence, rising and sinking across entire regions. It is like watching the Earth inhale from orbit. These radar images often appear as colored rings or bands, each band representing a tiny increment of motion. When you see many rings centered on a volcanic system, it suggests gradual swelling below. Not a spike, a curve. Not a shout, a posture. Posture is the right word. The land changes how it holds itself. Uplift does not automatically mean eruption. You rest with that reassurance. Many volcanic areas experience cycles of inflation and deflation, swelling and settling without ever erupting. Magma may enter a reservoir, increase pressure, then cool, crystallize, or migrate sideways. Fluids may accumulate, then escape through fractures. The surface responds, then relaxes. Breath in. Breath out. You imagine the crust as a flexible shell over a warm interior. Not floppy, not fragile, but capable of slow bending under load. Rock at depth can behave elastically over short times, storing strain like a compressed spring, and viscously over long times, flowing slightly to reduce stress. Because of this, uplift curves are often smooth, not jagged. Smooth curves calm the mind. They signal gradual change. The shape of uplift also carries information. A broad, gentle dome suggests a deep, wide pressure source. A tighter, steeper bulge suggests a shallower one. By modeling these shapes mathematically, scientists estimate the depth and size of the inflating region. Geometry becomes diagnosis. You do not need the equations. You keep the image, shape reveals source. Sometimes uplift is not centered exactly where older eruptions occurred. Magma pathways can shift. Reservoirs can grow in new pockets. The system is dynamic, adjusting to stresses and weaknesses in the crust. Old scars guide new motion. Faults and fractures act like pre-drawn lines in wood grain. The earth prefers existing paths when possible. There are also times when the ground sinks subsidence after uplift phases. This can happen when magma withdraws, cools, or degasses, reducing internal pressure. Hydrothermal fluids may drain. Cracks may open and redistribute load. The surface lowers again by small amounts, like a held breath released. You feel the rhythm: rise, rest, fall, rest. In some famous volcanic regions, these cycles repeat across decades. Historical records show alternating phases of inflation and deflation without eruption. Each cycle teaches scientists more about the plumbing below: how easily fluids move, how compressible the system is, how connected the reservoirs might be. Repetition becomes teacher. Tilt meters add another layer of listening. These are instruments placed on the ground to measure tiny changes in slope angle, so small that they register changes in microradians. If one side of a volcanic area rises slightly more than another, the tilt reveals direction and rate. It is like placing a marble on a plate and noticing which way it would roll. Slope becomes sentence. All these tools together, GPS, radar satellites, tilt meters, form a posture reading network. They do not predict by themselves. They observe. They provide continuous awareness of how the land carries stress. Observation replaces surprise with context. You let that feel reassuring. Watching is a form of care. Even temperature can contribute to surface motion. Heating expands rock slightly. Cooling contracts it. Seasonal groundwater changes can load and unload weight. Snowpack, rainfall, and erosion all add small signals that must be separated from deeper causes. Scientists filter these influences patiently, like removing background noise from a recording. Clarity comes through comparison. You imagine the landscape as a sleeping animal whose breathing you can now see not with your eyes, but with instruments. Each gentle rise is noted. Each settling is recorded. Nothing is rushed. No single breath defines the story. Only patterns across time. And as the ground lifts and relaxes in these slow cycles, another set of messengers often rises alongside the motion, invisible, weightless, drifting upward through cracks, gases carrying chemical hints from the deep, waiting for you to notice their quiet arrival. You settle your attention on something you cannot see. Not rock. Not motion. Not shape. This time, you listen for what drifts. What escapes. What rises without color or form. You turn your awareness toward volcanic gases, the invisible messengers that travel upward from deep systems, long before any surface change appears dramatic. You imagine the earth writing letters in vapor. Deep underground, within magma and heated rock, gases are dissolved under pressure. They are held the way air is held in sparkling water before the cap is opened. The deeper the pressure, the more gas can stay quietly mixed within the melt. No bubbles. No foam. Only hidden presence. The most abundant of these gases is water vapor, simple steam drawn from minerals and from recycled oceanic crust carried downward by tectonic plates. Even deep earth fire contains water in molecular form. You rest with that softness, heat and water together. Along with water vapor come other gases: carbon dioxide, sulfur dioxide, hydrogen sulfide, and smaller amounts of other compounds. Each has its own behavior, its own preferred depth of release, its own way of moving through rock. They are like different musical notes escaping from the same instrument. Not all at once. Not at the same pitch. When magma rises or pressure shifts, gases begin to separate from the melt. Tiny bubbles form, grow, and connect. If pathways exist, fractures, porous zones, fault lines, gases can migrate upward even when magma itself remains deep below. Travel does not require eruption, only connection. You picture scent moving through a house from a distant room. You do not see the source, but you know something is active because the air has changed. Volcanic gases often reach the surface through soil, through cracks, through geothermal features like hot springs and fumaroles, openings where steam and gas escape continuously. These emissions may be steady for years, even centuries. They are part of the planet's pressure regulation system, a slow venting. Venting is not violence. It is balance. Scientists measure these gases carefully. Some sensors sit directly in vents, sampling composition and flow rate. Others are carried by handheld instruments across the ground, detecting trace concentrations in soil air. Some measurements are taken from aircraft or satellites, which can detect sulfur dioxide clouds and carbon dioxide variations across wide areas. You imagine invisible ink revealed under special light. Each gas tells a different part of the story. Carbon dioxide tends to escape from magma at greater depths than sulfur gases. It is less soluble under pressure changes and often leaks upward first. An increase in carbon dioxide emissions can sometimes indicate deep magma input into a system, new material arriving below. Sulfur dioxide, by contrast, often signals shallower magma or active degassing closer to the surface. Because sulfur dissolves differently, its release pattern carries depth information. By comparing gas ratios, the relative amounts of different gases, scientists estimate where degassing is occurring. Ratios become clues. Chemistry becomes map. You keep it gentle in your mind. This is not code to crack urgently, but patterns to read patiently. Trends matter more than moments. A single measurement is a snapshot. A long record is a narrative. Gases also interact with groundwater on their way upward. They dissolve, react, and alter surrounding rock. Acidic fluids can change mineral structures, turning hard volcanic rock into softer, clay-rich material over time. These altered zones are signatures of long-lived gas pathways, footprints of invisible travel. Invisible travelers leave visible trails. Temperature influences gas behavior too. Hotter systems drive more vigorous circulation. Cooler systems release more slowly. Changes in heat flow can shift which gases dominate at the surface. Steam output may increase, springs may change composition subtly. Water becomes translator. Some volcanic lakes act as gas collectors. Carbon dioxide can dissolve into deep lake water and remain trapped under pressure layers. In rare cases, sudden overturning can release the gas rapidly, but you hold that knowledge calmly, as a special scenario, not a common one. Monitoring exists specifically to prevent surprise in such places. Awareness is protection. Measuring gases is not always easy. Wind disperses plumes. Rain absorbs compounds. Soil moisture changes readings. Instruments must be calibrated and compared. Data must be averaged and filtered. Patience again becomes the central scientific tool. You notice how often patience returns as the hero of this journey. There are even plants that help reveal gas emissions. In some volcanic regions, vegetation shows stress where carbon dioxide seeps through soil in higher concentrations. Roots receive less oxygen. Leaves change color. Growth patterns shift. Biology becomes sensor. Living things respond to invisible chemistry. Satellites now monitor certain gases globally, detecting sulfur dioxide high in the atmosphere. These measurements help confirm eruption plumes, but they also track persistent degassing from active systems. From space, invisible emissions become colored maps. You imagine the planet exhaling in slow motion, breath made visible through technology. Importantly, like tremors and uplift, gas release alone does not equal eruption. Many volcanic systems degas continuously without erupting. Degassing can even reduce pressure, acting as a stabilizing valve. Release can be relief. You let that feel reassuring, escape paths lower stress. Scientists look for coordinated changes, gas increases paired with seismic swarms, paired with uplift, paired with temperature shifts. Multiple signals together carry more meaning than any single one alone. Volcanic forecasting is like listening to an orchestra, not a solo instrument. Harmony matters more than volume. You rest now with the image of molecules rising through cracks, each one carrying information from depth, pressure conditions, melt chemistry, temperature state. Messages written in atoms. Letters written in vapor. You cannot see them with your eyes, but you can know they are there, moving, reporting, participating in balance. The deep earth communicates not only through motion and shape, but through breath. And as these invisible messengers drift upward and disperse into the sky, other records remain behind, solid, quiet, layered ash and stone laid down from ancient eruptions, waiting like archive pages for you to learn how to read them next. You slow your thoughts and turn from signals of the present to records of the past. Not memories in minds, but memories in matter. You imagine the ground beneath you as a library, not of paper and ink, but of layers and grains. Each layer holds a moment. Each grain holds a clue. You begin to walk, in your mind, across a landscape built from settled ash. When volcanoes erupt large or small, they send material into the air. Tiny shards of rock, mineral crystals, droplets of glass formed from molten spray. This material falls back to earth and settles in blankets that follow wind and gravity. Over time, these blankets become layers. Over longer time, layers become stone. Ash becomes archive. You kneel beside an imaginary outcrop, a natural wall where erosion has revealed stacked bands of different colors and textures. Some layers are pale and fine like flour. Others are darker and grainy like sand. Each band marks a separate eruptive event, a separate moment when underground processes reach the sky. You trace the layers with your attention like lines of poetry. Geologists call these ash layers tephra. The word is gentle and broad. It includes all sizes of erupted fragments, from fine dust to larger pumice pieces. Each tephra layer has a unique chemical fingerprint based on the magma it came from. That fingerprint allows scientists to match layers found in different places to the same eruption. It is like matching handwriting across distant letters. Even when layers are thin, only a few millimeters, they can be identified through mineral content and glass chemistry. Laboratories analyze tiny samples, measuring element ratios with precise instruments. Silicon, aluminum, iron, sodium, potassium, the proportions vary slightly from eruption to eruption. Variation becomes identity. You imagine each eruption mixing its own color palette, then dusting it across the land. Later, patient readers compare palettes and connect events across valleys, lakes, and even continents. A single ancient eruption can leave a timestamp layer spread across thousands of kilometers. One moment, widely written. Dating these layers brings time into the story. Some volcanic minerals contain radioactive elements that decay at known rates. By measuring parent and daughter isotopes, scientists estimate when crystals formed. Other layers are dated by their position relative to known climate records preserved in ice cores or ocean sediments. Clocks hide inside atoms. You hold the idea softly. Stone can tell time if you know how to listen. Not to the tick of seconds, but to the drift of isotopes. Not to calendars, but to ratios. The Earth keeps time chemically. Supervolcanic eruptions of the distant past are often first recognized through these ash records. A very thick, widespread layer hints at a very large event. When that same chemical fingerprint appears across multiple distant sites, the scale becomes clear. Breadth implies volume. Distribution implies height of the eruption column and strength of atmospheric transport. Spread reveals strength. But ash layers do more than mark eruptions. They also record environment. Pollen trapped between layers reveals what plants were growing at the time. Tiny fossils show what lived in nearby waters. Soil horizons between ash beds reveal quiet periods of stability and weathering. Silence leaves layers too. You picture a stack, ash, soil activity and rest alternating like breath and pause. The thickness of soil layers suggests how long the quiet lasted. Rich soils imply long calm intervals. Not all ash remains loose. With burial and groundwater interaction, ash can harden into tuff, a soft volcanic rock made of compressed fragments. Tuff can preserve delicate textures, flattened pumice, glass shards, crystal fragments. Under a microscope, these shapes reveal eruption style, explosive fragmentation versus gentle fountaining. Texture becomes testimony. Some crystals inside ash are older than the eruption that carried them. They formed earlier inside magma chambers and were later swept upward. These are called inherited crystals. Their internal chemical zones record pre-eruption chamber history, heating, cooling, mixing events. A single crystal can contain multiple chapters. Small objects, long stories. You imagine holding one crystal like a lantern slide, each growth ring a change in underground conditions. By analyzing these zones, scientists estimate how long magma resided before eruption and how quickly final changes occurred. Preparation leaves signatures at microscopic scale. Tiny rings, deep timelines. Ash layers also appear in ice cores drilled from polar regions. Fine particles carried high into the atmosphere settle onto ice sheets and become trapped in annual snowfall. Each year adds a new layer, sealing particles in place. When cores are drilled, Those layers read like barcodes of past eruptions. The sky writes onto ice. Matching ice core ash chemistry to ground deposits connects atmospheric records with volcanic sources. Climate scientists use these matches to study how large eruptions affected global temperature because sulfur-rich eruptions can reflect sunlight in cool climates slightly for a few years. Impact becomes measurable, not mythical. You keep the tone calm, effects are studied, quantified, bounded. Science turns awe into understanding. Numbers replace rumors. Records replace guesses. Lakes also preserve ash gently. Fine particles settle through still water and form thin, even layers on lake beds. Sediment cores pulled from these beds reveal uninterrupted timelines, quiet deposition punctuated by ash falls. Each ash line is a timestamp crossing ecosystems. Water keeps neat pages. By reading these many archives, rock outcrops, soils, ice cores, lake sediments, scientists reconstruct eruption histories spanning hundreds of thousands of years. Patterns appear, clusters, gaps, changing chemistry over time. Supervolcanic systems show long preparation eras between major events. Long waits dominate. You feel how this knowledge softens fear. The past is not hidden. It is documented in matter. The Earth has already written most of its autobiography. We are learning to read it carefully, line by line. Reading replaces guessing. You walk again along your imagined layered wall and feel gratitude for preservation. Without these records, the deep system would feel unknowable. With them, it becomes legible. Not predictable in detail, but understandable in behavior. Understanding is a form of calm. And as you step back from these stone pages and chemical clocks, you notice how much of this reading depends on instruments, microscopes, spectrometers, satellites, sensors, careful tools that extend human senses, and next you will sit beside those listening devices and learn how they help the planet speak in real time. You imagine yourself in a quiet observatory perched near a volcanic region. The walls are not lined with books or machines that hum loudly, but with instruments of attentive listening. Each device is a patient ear, a thoughtful eye, a subtle hand, reaching into the Earth's depths and into its whispers. You sit beside them, letting your senses settle into their rhythms. Seismometers are among the first instruments you notice. They look simple, sometimes just a small metal box with a weighted pen touching a rotating drum. But in function, they are extraordinary, sensitive enough to detect vibrations smaller than a human hair's width. They register tiny tremors, deep slumbers, and gentle creaks of rock adjusting to stress. Each line they draw is a heartbeat of the planet, a steady pulse recorded over hours and days. You watch these traces flow slowly across paper or digital screens. Some lines are short, sharp spikes, tiny quakes. Others are long, wavering undulations, harmonic tremors. You learn to see these lines as conversation, not alarm. Patterns emerge like motifs in music. Repetition, rhythm, variation, these are the language of motion, quiet and unhurried. Nearby, tilt meters rest gently on the ground. They measure subtle changes in slope, a fraction of a degree, revealing how the surface flexes and bends. They register a rising dome, a tilting flank, or a gentle bowing that is imperceptible to your eyes. Tilt is like posture, the land shifts slowly under the weight of forces below, breathing in tiny, deliberate movements. You imagine placing a hand on a carpet that rises imperceptibly. Feeling the change, sensing it without rush, noticing the direction. These instruments make the invisible tactile, measurable, communicable. GPS stations are anchored into bedrock, tracking minute movements in 3 dimensions. From day to day, centimeter by centimeter, you can see uplift or subsidence, horizontal shifts along faults, or slow expansion of a volcanic edifice. The land's subtle dance is now visible. The rhythm of the earth, previously hidden in stillness, becomes perceivable and interpretable. Satellites orbiting overhead contribute another layer. Radar and optical systems can measure surface deformation over vast regions. Repeated passes map elevation changes, creating colorful images where each band or ring indicates a tiny increment of motion. When viewed over time, these maps reveal swelling, deflation, or gradual tilting, like watching the planet inhale and exhale from space. You sit quietly, letting your mind follow the invisible currents, the deep pushes and pulls, the gases rising along fractures, the magma shifting slowly beneath. Instruments do not make noise unless you interpret it. Their language is subtle and patient. Observing them teaches stillness. Understanding arises from calm attention. Temperature sensors record warmth in soils, in vents, and along hot springs. Gas analyzers sample carbon dioxide, sulfur dioxide, and other emissions, revealing chemical shifts that signal deeper processes. Some instruments float above water or hover in the air, measuring plume compositions, wind patterns, and dispersion. You feel that observation itself is a gentle act of care. Instruments do not interfere, they extend awareness. They make the hidden legible, the slow discernible, the subtle concrete. Watching is an engagement of empathy and curiosity rather than fear. Each measurement is a note in a larger symphony of planetary behavior. Data from multiple instruments are often combined. Seismic tremors aligned with gas emissions and surface uplift create a more complete picture than any single observation. Cross-referencing instruments allows scientists to understand the relationships between phenomena, where magma moves, how gases escape, where the ground flexes, and how patterns evolve over time. You notice that the instruments have patience built into them. Some record continuously, others measure at intervals, and most store data for months or years. The Earth moves slowly compared to human attention spans. To understand it, one must slow down as well. You breathe with that tempo, matching the planet's quiet rhythm. Inside observatories, computers analyze signals in real time, but interpretation still relies on human experience. Scientists learn to distinguish natural variations from unusual events. They study how volcanic systems have behaved in the past, what signals preceded eruptions historically, and how similar patterns may manifest today. Long-term observation becomes as essential as acute measurement. You imagine the scientist's mind as a patient listener, reading faint tremors, rising gases, swelling surfaces, chemical nuances, synthesizing them like a gentle meditation on cause and effect. There is no panic, only careful attention. The instruments, with all their precision, teach a deeper truth. Volcanic systems are rarely silent, but their messages are slow, measured, and repetitive. They prepare rather than surprise. The Earth communicates through motion, heat, gas, and deformation, but it does so gradually, leaving time for listening and understanding. Even instruments themselves become poetic. Tilt meters bow like humble witnesses. Seismometers sketch delicate traces of vibration, rhythmic as a heartbeat. Gas sensors inhale and exhale silently, tracing invisible breaths. Satellites orbit like distant eyes, recording movements imperceptible from below. Together, they form a multi-sensory awareness that replaces fear with comprehension. You reflect on patience again. The planet has its own slow timeline. Signals may build over days, months, years, or decades. Some indicate no imminent eruption, others may foreshadow rare events far in the future. Monitoring is less about immediate prediction and more about understanding rhythms, identifying anomalies, and seeing patterns over time. The calmest realization settles over you. Knowledge itself is protective. Awareness allows preparation. Observation transforms uncertainty into insight. Instruments make the invisible visible, the subtle tangible, and the slow deliberate. They remind you that large systems, even supervolcanic ones, do not erupt without signals, and that those signals are often gentle whispers long before any dramatic event. You breathe in slowly and let the quiet responsibility of watching sink into your mind. You appreciate the stillness, the subtle communication, the patient orchestration of measurement. Each instrument, each line of data, each subtle pattern contributes to understanding the deep Earth's language. And as you sit beside these listening devices, you notice how the Earth has already provided long archives of past activity in stone, ash, and crystal, a record you have begun to read, and you sense that the next step is to explore why, even with all this observation, prediction remains delicate, dependent not on certainty but on respect for complexity and the patient unfolding of time. You sit quietly, surrounded by the hum of instruments and the patient records of past eruptions. The Earth has already spoken through tremors, gases, uplift, and ash layers. You have learned to read its subtle cues. And yet, you realize something profound. Even with all this knowledge, prediction is delicate. Not because the planet is secretive, but because it is complex. And complexity requires humility. You begin to think of the volcanic system as a living network, a web of interactions that stretches from the deepest mantle to the high clouds. Magma moves, but not alone. It carries heat, gas, crystals, pressure, and stress. Each variable interacts with the others in patterns that may amplify or cancel out. Nothing exists in isolation. Every action echoes elsewhere, often in subtle, unseen ways. You imagine a pond. A single pebble creates ripples. Two pebbles create overlapping patterns, sometimes reinforcing, sometimes muting. Now imagine thousands of pebbles falling at different times and places, and you begin to feel the intricacy of forces beneath a supervolcano. Scientists use models to make sense of this intricacy. They input data, the volume of magma, the pressure in reservoirs, the movement of gases, the thermal gradient, the historical patterns of eruptions. Equations simulate how these elements interact over time. But models are not prophecies, they are explorations of possibilities. They reveal probabilities, not certainties. They whisper instead of shout. You rest in the softness of maybe rather than the harshness of must. Sometimes models suggest heightened likelihood of unrest. Other times, they reveal stability in the very systems that seem most active. Even with sophisticated monitoring networks, rare events can defy expectations. Earth is patient, creative, and indifferent to human schedules. Its processes unfold over years, decades, centuries. You cannot rush its story. You notice how gently this realization lands. Not as a warning, but as a form of respect. Complexity demands humility, which in turn fosters careful observation. Patience becomes a scientific tool, not merely a virtue. You consider the analogy of weather. Just as meteorologists cannot predict the exact path of every cloud, scientists cannot always predict the exact timing of a supervolcanic eruption. Yet both study patterns, probabilities, and trends to understand underlying behavior. They learn from each season, each decade, each record. Knowledge accumulates. Insight grows. But absolute certainty is neither necessary nor possible. Patterns, like waves, become rhythm. Even when multiple warning signs align, swarms of small earthquakes, noticeable uplift, shifts in gas composition, prediction remains probabilistic. Each system has its own thresholds and internal variability. One volcanic reservoir may respond to pressure changes differently than another nearby. Eruptions are rare, high-energy events, and nature does not always follow a predictable script. You imagine walking along a gently swelling field, feeling the rise beneath your feet. It may continue without incident for decades, or it may eventually reach a tipping point. The uncertainty is not frightening, it is simply part of the system's natural rhythm. Your mind softens around it. Time itself is a variable. Magma may spend centuries in a chamber before conditions align for eruption. Crystals grow slowly, gases accumulate gradually, rock bends almost imperceptibly. Signals may emerge for years without any dramatic outcome. Not every tremor leads to eruption. Not every uplift dome signals crisis. Observation, record-keeping, and analysis are what allow humans to respond wisely. You feel the patience of science as a companion. Observation replaces fear with understanding. Each measurement contributes to context. Each pattern noted refines probability. Even errors or unexpected deviations become lessons for future awareness. The system teaches by example, not admonition. You consider the role of human perception in this process. When warnings are issued, or caution is advised, it is not a statement of certainty. It is a measured, thoughtful response to probability. Agencies communicate risk ranges rather than fixed dates. This careful communication is itself a form of listening, ensuring that attention is guided without panic. Listening is as important as measuring. Sometimes, the most delicate part of prediction is acknowledging limits. Honesty about what is unknown is a strength. It prevents overconfidence, encourages continuous observation, and maintains respect for natural complexity. You breathe in that honesty, feeling how it soothes as much as informs. Uncertainty, reframed, is calm. You also notice the role of feedback. As new data arrive, models are updated. Predictions shift. Early assumptions are corrected. This is not failure, it is a natural, healthy response to dynamic systems. Science is iterative. Understanding deepens through repetition, reflection, and refinement. Knowledge grows as questions are refined and answers tested over time. The system is alive in its responsiveness. You imagine a slow conversation between humans and Earth. Tremors, gas, deformation, heat, ash, the planet speaks. Scientists observe, measure, interpret, and refine. models articulate likelihoods, not commands. Humans respond with preparation, not panic. The dialogue is calm, patient, continuous. Learning becomes the act of listening deeply. Even rare, dramatic events, supervolcanic eruptions, follow physical laws. Energy must accumulate, pathways must open, thresholds must be reached. Understanding these thresholds requires synthesis of multiple types of information. Observation, both historical and real-time, allows scientists to estimate how these thresholds may be approached. Still, prediction is always a soft probability, never a promise. You rest with this nuance. Safety arises from awareness, not certainty. Delicate prediction also involves scale. While short-term precursors may hint at near-future changes, long-term understanding requires examining patterns across centuries. Ash deposits, lava flows, and past uplift cycles provide context. Only by situating present signals within the long memory of Earth can probabilities be meaningfully assessed. Time is both friend and teacher. You notice how this lesson mirrors your own inner rhythm. Just as the Earth moves slowly and unpredictably, so too must understanding. Patience, attention, and respect for complexity allow insight without alarm. You are learning to inhabit the slow pace of nature, appreciating subtle signs and reframing uncertainty as a form of calm awareness. You imagine the Earth as a careful storyteller, offering chapters gradually, leaving space between them for reflection. The storyteller does not rush. Neither must you. You feel your mind settle into the quiet of probability, the gentle sway of uncertainty, the beauty of observing systems too large and slow to be dominated by haste. Each signal, each measurement, each minor tremor is a note in a symphony too vast to hear all at once, but perceptible to the patient listener. And as you absorb this understanding that prediction is delicate not because of danger, but because of intricate, interconnected processes unfolding over immense time, you begin to sense the next lesson, how the planet gathers all its signals, repeating, layering, and combining them, before it ever roars. Listening carefully, you will see how warning signs emerge long before eruption. You take a deep breath and imagine standing on the edge of a volcanic region, surrounded by the quiet instruments, the layered ash, the slowly rising land, and the invisible gases you have learned to read. All these signals, tremors, uplift, chemical messengers, historical layers, converge in your mind. They form a symphony, a vast composition of Earth's quiet communications. Each note is soft, measured, intentional. The planet does not roar without warning. It whispers first, in patterns you can learn to recognize. You picture the tiny earthquakes of swarms as individual taps on a distant drum. Alone, they might seem meaningless. But together, rhythm emerges. A sequence of taps over days or weeks forms a motif, a language of pressure and adjustment. Your attention, patient and steady, begins to hear the music beneath the ground. The slow rise of the land adds another layer of this symphony. Gentle uplift domes the surface like a sleeping chest, breathing softly over months and years. Combined with tremor patterns, the rising ground reveals not just activity, but direction, magnitude, and history. The Earth communicates in multiple dimensions at once: motion, sound, shape, and change. Gases drifting upward are like the faint scent of an instrument played in a hidden room. Carbon dioxide, sulfur dioxide, steam all rise through cracks, carrying information about depth, temperature, and pressure. They move silently, but the instruments capture their presence, transforming invisible movement into tangible signals. Each emission is a letter, a message, part of the conversation. Even ancient ash and stone contribute to the story. Layers of tephra, hardened tuff, and embedded crystals are pages written long before you arrived. They describe what the system has done before, what patterns repeat, what behaviors tend to emerge over centuries. The past teaches patience, showing that the Earth's signals are consistent across time, if you know how to read them. You begin to see these layers, both physical and instrumental, as a continuous timeline. Tremors, uplift, gases, ash, and crystal growth do not exist in isolation. They interact, overlap, and reinforce each other. One signal may be small and subtle, but together, the ensemble forms a narrative of stress, movement, and preparation. The Earth is patient, but persistent. Patterns are the key. Small earthquakes repeated over weeks, combined with gradual uplift and a subtle shift in gas ratios, often precede larger changes. Historical data show that supervolcanoes have built pressure over millennia, occasionally releasing it in enormous eruptions. Yet the majority of time, the system adjusts quietly, venting gases, reshaping internal magma chambers, and redistributing stress without catastrophic release. Signals exist not to frighten, but to guide. You imagine this communication as a series of refrains in a song. The Earth repeats certain themes, sometimes changing the key or tempo, sometimes layering motifs atop each other. Instruments allow humans to perceive this music, to track variation, to understand when a pattern is routine and when it might be exceptional. Observation becomes a form of empathy. Even seemingly random tremors or gas spikes have context. A single seismic pulse may be trivial. A single gas anomaly may reflect local weather or groundwater movement. But when you combine multiple signals over space and time, swarms aligned with uplift, shifts in gas composition paired with thermal anomalies, the meaning becomes clear. Patterns are the Earth's sentences, and understanding comes from reading them together. Your mind relaxes into this clarity. The Earth is not capricious, it is consistent in its communication. It teaches, warns, and informs. Listening carefully allows response without alarm. Preparation is the product of comprehension, not panic. And comprehension arises from attention, from patience, from respect for subtlety. Historical eruption records reinforce this lesson. Supervolcanoes do not erupt spontaneously. Evidence shows swelling, tremors, degassing, and chemical shifts long before major events. Ancient ash layers, correlated with tree rings and ice cores, reveal long sequences of precursory activity. Even when events occurred tens of thousands of years ago, the signs were present for those who could observe them. You hold this thought gently, the Earth provides notice. It signals, it nudges, it breathes. Catastrophe is not a surprise, it is a culmination of patterns, a crescendo in a long symphony of interactions. For humans, the lesson is simple: attention, care, and listening are the most powerful responses. Technology extends perception. Seismic networks, GPS stations, tiltmeters, satellite imaging, gas analyzers, and temperature sensors together provide a multi-dimensional view of activity. They capture tremors too small to feel, uplift too subtle to notice, gases too light to smell. These instruments do not act alone, they communicate with one another, and with scientists, creating a real-time dialogue between humans and Earth. You feel the intimacy of this connection. Observing is not intrusive, it is participatory. Every recorded vibration, every measured rise, every analyzed gas sample contributes to understanding. Data are not mere numbers. They are stories, insights, and patterns waiting to be heard. In listening deeply, you participate in the care of the planet's narrative. Even with the most careful monitoring, uncertainty remains. Earth is immense, complex, and variable. Signals may shift, combine in unexpected ways, or be subtle for decades. Yet the goal is not perfect prediction. The goal is informed awareness, seeing when the system behaves unusually, understanding trends, and recognizing the slow emergence of risk. Knowledge, rather than fear, guides action. You imagine standing in the middle of a vast orchestra, instruments scattered around, each playing faintly, their music weaving into a coherent whole. You do not control the music. You listen. You learn its language. You anticipate themes, but never dictate their arrival. The Earth's signals are both delicate and deliberate. The patient voice of the planet teaches rhythm, scale, and proportion. Swarms, uplift, gases, ancient layers, all are threads in a tapestry that spans space and time. By weaving these threads together, you form a picture that is both rich and gentle, revealing the planet's behavior without invoking panic. You sense a new layer of understanding. Warning is not alarm. It is communication. The planet whispers first, nudges subtly, repeats messages, and tests attention. Each signal is a word, each pattern a sentence. Those who listen carefully can respond with preparation, mindfulness, and calm respect. And as you integrate all these messages into a single, quiet mental image, you notice how the Earth has already prepared not only its warnings, but also its rhythms of adjustment. You begin to feel that the next chapter of your journey, returning to the surface, resting on a living, breathing planet, will carry the comfort of awareness, the security of knowledge, and the gentle reassurance that the Earth communicates constantly, softly, and with patience. You step gently back onto the surface, carrying all that you have learned. The whispers of tremors, the gentle rise and fall of land, the invisible messages of gases, and the stories preserved in ash and stone remain with you, layered in your mind like a soft blanket. Each piece of knowledge folds into the other, forming a map of awareness rather than fear. You are no longer just a visitor, you are a careful observer, attuned to the rhythms of a living world. The ground beneath your feet no longer seems inert. You feel it as a dynamic entity, breathing in slow, deliberate movements. Mountains and valleys are not static, they stretch, compress, and respond over centuries and millennia. Even when motion is imperceptible, it exists. You imagine every particle of rock subtly shifting, accommodating the forces that flow beneath, like cells in a patient organism. You feel gratitude for the quiet intelligence inherent in the planet's structure. The Earth communicates constantly, but its voice is calm and methodical. Unlike the suddenness of human alarms, its signals are gentle, patterned, and extended over long durations. Small tremors, gradual uplift, gas emissions, and subtle thermal changes are all part of a dialogue, a conversation in slow motion. You feel attuned to these messages, not with urgency, but with presence and patience. Awareness transforms uncertainty into comfort. You understand that the world can be both dynamic and safe. Supervolcanoes, with all their potential energy, do not erupt without long sequences of signals, whispers, nudges, and repeated motifs. Observing these patterns allows you to sense risk, but also to recognize stability. You rest in the knowledge that preparation, understanding, and careful listening are the most effective safeguards. You imagine the land as a living chest, inhaling and exhaling gently. Rivers carve soft lines into valleys, glaciers sculpt slow corridors in mountains, and soils accumulate layer upon layer over time. Even decay and erosion are part of this breathing cycle. Life adapts to these changes, finding equilibrium in the subtle adjustments of the world around it. You are part of this equilibrium too, safely cushioned on its surface, supported by the collective patience of geological time. The history you have explored, ash layers, crystal growth, past eruptions, provides a framework of perspective. You realize that supervolcanic events, while monumental, are rare, spaced across tens or hundreds of thousands of years. Most of the Earth's movements are gentle, cyclic, and restorative. Knowing this allows you to sit with a sense of calm, observing the planet as it nurtures balance while containing immense energy within its depths. You reflect on the instruments that extend human senses: seismometers, GPS stations, tiltmeters, gas analyzers, and satellites. They act as patient companions, translating imperceptible phenomena into observable information. With their guidance, the Earth's quiet communications become legible. You recognize that awareness, rather than absence of motion, provides security. You feel the comfort of being informed, not alarmed. The planet's invisible messengers, gases rising through cracks, subtle thermal shifts, faint chemical signals, carry insights from deep below. You sense these messages, not with anxiety, but with respect. Each molecule, each emission, each pattern is part of a narrative of equilibrium, resilience, and preparation. The Earth's deep processes are patient. They unfold at their own pace, allowing those who observe carefully to participate in a dialogue of understanding. Walking through imagined landscapes layered with ancient ash and tuff, you feel connected across time. Past eruptions, long dormant, have left records that enable interpretation and insight. Each layer tells a story of preparation, release, and recovery. The Earth keeps meticulous records, and by reading them, you participate in its long memory. You feel that the planet is not only alive, but self-aware in its own rhythms, teaching patience and humility. You sense the subtle interplay between present signals and historical context. The Earth demonstrates that patterns repeat, that signals can be interpreted, and that preparation is possible. Your mind integrates these lessons into a cohesive understanding. You realize that science is not an attempt to control, but an invitation to listen, observe, and respond mindfully. The landscape itself is a teacher of rhythm. Slow tremors, gradual uplift, and continuous degassing are all expressions of balance. By observing and understanding these rhythms, you gain insight into the dynamics of the Earth. Knowledge becomes a form of comfort. Observation becomes meditation. Awareness becomes reassurance. You imagine clouds forming above mountains, rivers winding through valleys, forests stretching across hillsides. Each of these systems interacts with the ground, with air, with water, with life. Even inanimate rock participates in cycles of energy, movement, and transformation. The world is vibrant, alive, and sustaining, and you are safely part of it. The planet's supervolcanoes, with all their potential power, are contained by processes that are visible, measurable, and interpretable. You understand that extreme events are preceded by long sequences of gentle signs, tremors, uplift, gas emissions, chemical changes, and historical repetition. By noticing these, you are already connected to the protective intelligence inherent in the earth. You are calm, attentive, and aligned with the slow, deliberate patterns of the living world beneath you. And as your awareness drifts gently toward rest, you carry with you the knowledge that the earth is alive, dynamic, and communicating. It cradles all life, including you, in a balance maintained through patience, resilience, and gentle rhythm. Each layer, each signal, each message is a part of a story that unfolds over time. You close your eyes softly, letting the steady, quiet heartbeat of the planet soothe you into sleep, while the gentle promise of continued observation lingers, a calm reassurance that even beneath your feet, the world is alive and gently holding you.